Yeah, it's. I have the honor and the pleasure to chair this session, the last one of our meeting, and I have also the pleasure to introduce Michael Miller from Toronto, who will tell us about epistemic and semantic effective realism. The floor.
Thank you. Okay, so I'm going to be talking about a new kind of approach to some of the questions that have been under discussion throughout the conference. And in particular, it's a new approach to scientific realism, which aims to kind of, in a way, shoot the gap between, on the one hand, empiricism, and on the other hand, realism. And the newness of the approach stems partly from the fact that it's based on, new in some of the relevant timescales at least, new developments in physics, which I think, or I'm going to kind of point to various ways in which I think amount to novel approaches to specifying the structure of a scientific theory. And attendant to those novel approaches to articulating the structure of the scientific theory come along new motivations for new approaches to interpreting the theory, and in the end, new approaches to thinking about what it would mean to take that theory to be a faithful description of physical reality. Okay. So that's where we're headed, but I was thinking about all of the various ways in which this new kind of approach to theory specification and interpretation connects to the themes of the conference, and I was reminded of a paper that's been much discussed, rightly so, in recent years, and particularly this passage, which has often been quoted. It's a very rich paper, very subtle paper of Stein's. And I just want to point to this in particular to show that while the approach to realism that I'm going to be discussing is, I think, new in some sense, the problems that motivate the approach are not new. They're the same old problems that we've been wrangling with for a long time. Okay. So here's Stein. Why should we say that the old term ether failed to refer, and that the old term atom did refer? Why that is, except for the superficial reason that the word atom is still used in textbooks, the word ether is not. It would be possible to do a lengthy dialectical number on this. Wayne did one, I highly recommend. But in brief, Stein says, our own physics teaches us that there is nothing that has all the properties posited by 19th century physicists for the ether or for atoms. But that, on the other hand, in both instances, rather important parts of the 19th century theories are correct. Okay, so Stein's observing, we take atom to refer, we take ether not to refer, or to have been one of these purported failures of reference involved in the pessimistic meta-induction. That's supposed to undercut the inference from the success of your scientific theory to its approximate truth or the genuine reference of its central theoretical terms. And he's saying, look, both the notion of the ether and the notion of an atom were tracking certain features of what's there in the physics correctly. And similarly, both of them, in some sense at least, in their 19th century incarnation, failed to track some of those features. And so they seem to be actually on a par. And this category of, or this notion of reference, which has become central in these discussions of scientific realism and adjudicating whether we ought to commit to a version of realism, doesn't seem to do justice, or doesn't seem to track the fact that both of these notions get some stuff right and some stuff wrong. He continues with a brief historical example in between. then says, the two cases, that of the ether and that of atoms, are, in my view, so similar that the radical distinction made between them by the referential realist confirms in me the antecedent suspicion that this concern for reference and associated with it, another Quinian motif, the concern for what is called the ontology of theories, is a distraction from what really matters. Okay, so Stein in the end wants to say, reference isn't the right kind of question to be asking when you're asking yourself what it is that are, whether or not the terms in the theories refer isn't the right kind of question to be asking when you're trying to sort out whether or not the theory is getting at the world in the way that the realist wants to commit to. So ultimately, what I'm going to be trying to say here involves some kind of reference like commitments in the modern new approach to interpretation and in realism that I'm going to advocate for. And so in that sense, I think I'm coming apart from what Stein is advocating for here. But my motivation for doing that is that I think that Stein is absolutely right, that whatever kind of reference-like notion is going to function in our characterization of realism, one which counts 19th century Adam's notion, the term atom as referring, and 19th century term ether as not referring, isn't tracking the salient issue at hand. Okay. So, one way to say that more sharply, I guess, is just that the conception of reference that has been appealed to in discussions of scientific realism, I don't think is really fit for purpose. We want a notion like reference that's keeping track of when the terms in the theory actually are labeling items that in the world. But the demands of the ordinary kind of notion of reference coming from the philosophy of language is too stringent to actually keep track of the relevant notion when we apply it in the context, at least, of scientific vocabulary. Okay. So that's by way of connecting this to some of the themes that we've been discussing here. On the path to this new version of realism, I want to first just kind of disambiguate the way some central terms are getting used. They've changed and shifted and get appealed to differently by different people. I'm going to tell you how I'm going to talk about them here. Then I'll give you a first pass of this new version of scientific realism, effective realism, and I'll draw what I think is an important distinction between different varieties of this view that have grown up in the literature, and I'll briefly conclude. Okay. So, the interpretation of a theory presupposes that we've specified the structures constitutive of that theory. Okay. Hopefully that's relatively uncontroversial. So if I present you some theory that I want to start to interpret, usually the way I present that to you is I hand you a collection of mathematical structures. I say, here's the theory. And once you've got a collection of structures fixed, then an interpretation is the kind of thing that associates physical content with those structures. And there's lots of different ways, and lots of different people have lots of different ways of thinking about what the rules are for getting from a collection of mathematical structures to the articulated physical contents that are supposed to be associated with those structures. Okay. Realism, on the other hand, presupposes interpretation. So once physical content gets associated with a collection of structures, once you've done the interpretation step and you make your mathematical gadgets about physical things in whatever way you prefer to do that, then a variety of realism commits to agreement between at least some of that physical content and the world. Wholesale realism would say that all of that content agrees with the world. So-called selective realisms, of which effective realism is one, are realisms which say only part of the physically interpreted content that my interpretation associates with the structures of the theory agrees with the world, or do I have good grounds for thinking agrees with the world? Okay. So that's all just by way of clarifying terminology. Now, problems at the foundation of quantum field theory, which have persisted pretty much throughout, come on in, Carl, have required the development of new tools for the very first stage in this kind of bootstrapping procedure up to a scientific realism, namely the structure specification phase in quantum field theory has looked, I think at least, people the more historically minded in the room can correct me if I'm wrong, it's had a long drawn out structural specification phase. Many theories have in their infancy a phase where it's not clear which mathematical structures are going to be the ones constitutive of the theory, and there's discussion of that. But typically, we arrive at some agreed upon core collection of mathematical structures which are constitutive of the theory, and then subsequent developments build on top of that. In the case of quantum field theory, that story is a story that, after now nearly 100 years of development, continues to this day. And in many ways, depending who you talk to, depending who you ask how to characterize a quantum field theory, you're likely to get one of a number of different stories about what sorts of structures are the right ones for characterizing the content of the theory. Okay, so consequently, the debates about the interpretation of quantum field theory have really been debates about structure specification. They've been debates about how to think about which of these various kinds of articulations of the mathematical structures constituted quantum field theory ought to be the basis for an interpretation. We've made, and I say this having somebody participate in this, what feels like embarrassingly little progress with the next question, which is the thing where once I've got a structure, even if it's one amongst many, how do we tell our story about what the physical content that's supposed to live on top of that? So if you compare discussions of the interpretation of quantum field theory to discussions of the interpretation of, say, non-relativistic quantum mechanics, you'll notice that they're wildly different in character. In the non-relativistic quantum mechanics case, we get detailed stories about what the world's characterized physically, according to that theory, are supposed to look like, and then those become candidates for realist commitment. In the case of quantum field theory, we have little bits and pieces of that second step. There's discussions of, say, whether we ought to associate physical content in terms of particles or fields, but even the discussions of that sort of question are still relatively unsettled. And partly that results, I think, from the fact that different authors in those debates proceed from different assumptions about the underlying structure specification phase. Naturally end up at different verdicts about questions like whether they're particles or fields. And even if you were to resolve that question somehow, I think there's a lot more to say about the interpretation step in interpreting quantum field theory. So that's just the first two pair of steps. But then the second step, I said, is once I've got an interpreted theory, telling you we don't have it yet in the case of quantum field theory, or at least not to my level of satisfaction. But now I'm telling you that there's a new form of scientific realism that's grown up, and I told you that realism is supposed to be a thesis about the relationship between an interpreted theory and the world, and an agreement between those two things. And several philosophers have argued that a kind of novel approach to structure specification that I'll tell you a bit about in just a moment, in the context of quantum field theory, namely effective field theory, leads to a novel form of realism, effective realism. And this long kind of preamble is just to say, I'm ultimately sympathetic to the idea that the tools of effective field theory are going to be helpful for that task. But I don't think we have yet all of the pieces in place to tell a full-blooded realist story. And part of what I'm going to be telling you here is what I take to be missing from what's been said already. Okay. So before I tell you my kinds of qualms about what's done so far, let me just say, I'd say the reception of effective realism has been mixed. There's been, I think, a fair amount of excitement about this kind of view, but there's also been more critical reactions. On the one side, some have worried that effective realism collapses into merely saving the phenomena. It fails to distinguish something that isn't just an empiricism and not itself a realism. While others have worried that the content of the effective realist thesis remains underspecified. Just haven't said enough yet about what the content of the interpreted theory is supposed to be in order to judge whether or not it matches on to the world. And there's also disagreement, even amongst advocates of effective realism itself, about how to characterize the view. So if you look at the literature on this topic now, there's maybe a dozen papers or so, and you look at what view people are calling effective realism, they're not all mutually consistent with one another. People have different ideas of what's going on, what actually the tools of effective field theory are supposed to be getting you in terms of a realist view. And so that's, I take it, the state of discussions of this view. What I'm going to offer here are just the identification of two sorts of choice points that I think are critical. And I think these are the critical choice points on the path to an adequately specified effective realism. The first choice concerns which principles of interpretation to adopt. So the step that gets you from whatever structure you're going to reify as the basis for your interpretation to the physically interpreted content. And the second choice concerns the content of the realism, the thesis about given that interpreted structure, what do I think I'm warranted in believing about agreeing with the world? So the novel approach to structure specification that we get from effective field theory doesn't do much to fix our approach to interpretation. And this, I think, has kind of gotten lost in the shuffle, in the excitement about what effective field theory was going to do in service of this new kind of realism. But I'll show you in a moment the very rough contours of what these new tools are and why people have been motivated to use them in elaborating the form of realism. But what I'm going to observe is just those tools themselves are not the right kinds of tools to tell you what the physical content of the theory is. You've got to come with, at most, they kind of generate some constraints on what that physical content could be, and they generate those constraints by constraining what sorts of structures could be the substrate on which the interpretation gets generated from. But on the assumption that an approach to interpretation is already fixed. So if you've got some independent view about how to go about associating physical content with mathematical structure, it does, however, these new tools of effective field theory do, however, provide resources that are helpful for articulating two distinct kinds of realism. So assuming we've got some background operative principle that gets us from our mathematical structure to our physical content, there's then a new choice point, which the tools of effective field theory are helpful for working through. In terms of which of these two distinct kinds of realism one wants to adopt. So by the end of the talk, I don't think, I'm not going to fully specify any effective realist thesis because, as I've said, the tools of effective field theory don't give us the resources that we need to generate an interpretation. So the effective realist thesis will still be underspecified because to play this game, you've got to come to me with an established background set of interpretive principles. I know at least half the people in this room, I'm certain, already have their own way of thinking about that sort of question, and they're often wildly different from each other. But my aim is, by identifying the choice points here, my aim is to put some structure on the what I think is a space of effective realisms and to isolate more clearly what there remains to be filled in, and to actually generate fully specified versions of this new thesis about scientific realism. Okay. So let me give you a first pass. And this is just aimed as a way of saying how we got to effective realism. So one of the central conceptual innovations of the effective field theory framework is the explicit representation of the boundary of applicability of models in their mathematical expression. So one of the conceptual developments is that we now go from taking theories unrestricted in scope and explicitly modeling a restriction in scope of the theory directly within the mathematics of the theory. And I want to show you a little bit about how that comes to be in effective field theory. So it's important to note that I think this is where a lot of the confusion surrounding these views stems from. The historical route to that innovation was really circuitous, and we get different versions of the historical story about how it came to be. The initial steps toward it were motivated by the presence of perturbative ultraviolet divergences, which were thought to signal the breakdown of models at short distance scales. And so this is if you start looking at the literature on QFT, in the physics literature, you'll frequently encounter this claim that perturbative level divergences in an expansion that I'll show you in a moment are a signal that the theory is, in some sense that requires further specification, going to break down. That motivated people to think about why we were getting these infinities at the level of the perturbative expansion. So you can specify a model, for my purposes, of quantum field theory with a Lagrangian. So perhaps it's worth saying there's different approaches to structure specification, as I noted earlier. This is the kind of approach to structure specification that one gets in approaches to field theory in particle physics. There's other approaches to structure specification which are partially connected to this, in the sense that there are certain kinds of mathematical connections between the various approaches. I'm not going to elaborate on those here, though I don't take what I'm saying here to be exclusively relevant to these kind of particle physics type approaches. I think there are stories you can tell about how to get back to the other mathematical approaches to field theory, at least under restricted conditions. Okay, so we specify a Lagrangian. That's going to include things like what sorts of fields there are, what sorts of interactions those fields enter into with respect to one another. Here, lambda parameterizes the strength of an interaction between the only fields in the problem, and the lambda equals 0 case corresponds to the exactly solvable free theory. So the difficulties in quantum field theory come from the fact that exact solvability, or part of the difficulties at least, come from the fact that exact solvability that we get in the case where there is no interaction term is relatively rare. That happens under very special circumstances. It happens when there is no interaction, or when the number of space-time dimensions is reduced relative to the actual number of space-time dimensions, namely 4. And so in those cases where we have exactly solvable theories, you can do structure specification in a way that looks a lot like so-called normal structure specification. You can do the kinds of things that philosophical stories about scientific theories standardly say about what it is to be a theory, what it is to present a theory, demand of scientific theory. Free quantum field theories look pretty much like that. And if those were the only quantum field theories that we were concerned with, there was a counterfactual possible world where we would never have come to this effective field theory generalization. In fact, I think the effective field theory generalization of the structure specification for QFT turns out to be a kind of happy accident. And I'm going to try to give you a sense of what the nature of that happy accident was, because it's a solution to a problem different from the one it was initially reacting to. Okay. So, but once we have the interaction term and we don't have an exactly solvable theory, what do we do? Well, we hope that the coupling is small. And so, sorry, I'm getting a little bit ahead of myself. So at this point, in addition to the free theory being exactly solvable, at this point, the domain of applicability is totally unrestricted. That theory I just wrote down to you makes claims under, it makes claims about arbitrarily short distance and infinitely high energy, as well as infinitely long distance and arbitrarily low energies. There's no restriction on the scope of the validity of that theory anywhere. It talks about the smallest bits of the universe and the biggest bits. So that we haven't fed in from the outset. When people set out to characterize quantum field theory from the outset, there was no restriction on the scope of the theory. So when the coupling parameter is small, we can develop the theory perturbatively. This is the standard kind of Feynman diagram expansion you've probably seen if you've looked at QFT at all. And so you get an expansion in the powers of the coupling parameter. But the integrals for the coefficients are perturbatively ultraviolet divergent. So let me show you what I mean by that. So we're set out to calculate terms corresponding to contributions to some given physical quantity in our theory. Many of there's different kind of patterns of divergent behavior, but many of the simplest cases that we compute initially diverge logarithmically in the very high momentum, very large energies, in the sense that if you integrate them up to a large cutoff, lambda, the integral looks like dk over k, and so the integral, when cut off with this parameter lambda, looks like log of lambda. And so if we let lambda go all the way to infinity, this thing is going to diverge on us. But for any finite value of the cutoff, we keep the integral finite. Okay. So that's the basic stopgap measure that gets loaded into QFT right when people realize that some of these expressions that we're writing down and trying to calculate with are giving us infinity rather than some finite value. Okay. That cutoff has been the source of much discussion. And it plays a critical role in discussions about how to think about effective realism. But on many, in many of those discussions, the way to think about that cutoff is something like, and I'm going to try to get more sharp about the different ways to say exactly how to think about lambda. But for now, you can just think about saying, look, theory, I care about what's happening in the field up to this level of energy. It's okay if you don't try to keep track of what's happening in the field with energies above that energy where I've cut things off. Or if you prefer to think spatially, look, theory, I want you to tell me what's going on in the theory above this minimum distance that I'm introducing into my theory. I don't even try to keep track of what's going on at distances shorter than that, okay? That's, in loose talk, what the cutoff is doing there at the level of the mathematics of the theory. It's telling the theory what parts of what's going on in the field, given the Lagrangian that we specified in the nature of the interaction in that Lagrangian, it's telling the theory what goings on described by that Lagrangian the theory really has to keep track of. And we're getting rid of part of what we initially asked the theory to keep track of, because when we were initially asking it to keep track of those things, it was seeming to have trouble. It was giving us infinity rather than a sensible number that could be the value of the quantity that we're calculating. Okay. So, what did I start?
You've been speaking for half an hour.
So in some models, it turns out to be possible to cancel the divergences by re-expressing that original Lagrangian in terms of a new set of renormalized quantities. So we just like add back new quantities into the Lagrangian, we change the theory. We do so in a way that takes measured input from the world. So there's an interesting alternative version of this talk where we focus on the way that the empirical information is getting loaded into the theory. So really, this is a process by which we make the theory match on to certain aspects of the data. This is not yet anything to do with effective field theory. This is standard counter-term renormalization. I show you just to give you a sense that we can systematically kill off those divergent terms by adding more divergent terms, which cancel them. And by replacing the original divergent integral expression with a regulated convergent intermediary, and by integrating up to a large but finite momentum value cutoff rather than infinity, one can fix the counter-term parameters so that the part of the coefficient at order lambda squared, which diverges as the cutoff gets removed, is canceled. And this trick is to do that order by order through the entire perturbative expansion in such a way that if a theory is what was originally thought to be well-behaved, perturbatively renormalizable, a finite amount of that will eventually be sufficient to make the entire perturbative expansion finite, order perturbation theory. The renormalization group is an additional added wheel that gets added on top, which characterizes how the couplings change with the energy scale. Okay. And effective field theory is a big group of techniques. It's not a clean individual mathematical structure or anything like that. It's a group of techniques. It's a collection of recipes that systematizes and generalizes this approach to the renormalization of quantum field theory models. Okay. And those tools, the tools of effective field theory, can be used to determine whether a given model has a well-defined UV continuum limit. And it turns out that that's just a model by model question. Some models do, some models don't. The best available evidence suggests that things like quantum electrodynamics, the first quantum field theory, and the standard model, the quantum field theory that we think is empirically adequate, the best evidence we have suggests that those do not have such continuum limit, meaning that they can't be theories that have unrestricted validity. We need something like the cutoff to stop the theory from trying to keep track of things which it can't keep track of. They don't admit of a consistent continuum generalization. The tools of effective field theory can also be used to study how sensitive the low energy long distance regime is to high energy short distance regime. So with these tools, we can ask a theory to give us something less than a complete description of what there is across all distance scales. So the fact that something like the standard model doesn't have a continuum generalization turns out to be, from the perspective of effective field theory, not totally devastating. We can still reason with the standard model perfectly well, despite the fact that it doesn't have this continuum generalization. And instead, we can ask what there is, according to the theory, on the limited range of scales across which the theory yields a coherent physical picture. In some cases, you can use effective field theory to show that the long distance or low energy physics turns out to be insensitive to the short distance high energy physics. And that insensitivity comes in quantifiable degrees. It's not usually the case that it's completely insensitive, but however insensitive it is, we can get a quantitative measure of that. Okay. And effective realism on a first pass is just the view that we should be realists about whatever that long distance, low energy physical content is. This is motivated by the fact that that's the part of what the theory says to which we have empirical access. That's the part of what the theory says where we can go out in the world, invoke and prod and test, and we can see if I scatter electrons off one another in a given energy range, do they behave according to the predictions of the effective field theory treatment of quantum electrodynamics, yes or no? If they do, this gives us a way to be realists about that part of the theory where we've got empirical access, and then that's where the intuitive kind of gloss on what effective realism is supposed to be stops. And I think you should be left thinking, okay, but I've got a lot of questions. And there's a lot of questions because on this first pass gloss on what effective realism is supposed to say, it's not so clear what our attitude is supposed to be about the structure, the mathematical structure that we started with, outside the boundary of applicability that we introduced into the mathematics of the theory. Okay, and final aside of this section, once we have effective field theory in hand, we can treat theories effectively, independently of whether they need to be treated as effective in order to be well-defined, like I've argued the stance of the model is, and in fact, independently of whether they're quantum field theories. You can use this technology, once you've got it in front of you, to do lots of different things and lots of different theories. Once you start modeling boundaries of applicability inside the mathematics of the theory, it becomes a powerful tool in and of itself, which doesn't require, for motivation, the presence of anything having to do with ultraviolet divergences to be present for the theory. Okay. So, here's the critical choice, I think, that partitions the various views that have fallen under the effective realism banner in the contemporary literature. How do we interpret the structure outside the domain of applicability? So one option is to just hold fixed our interpretive principle and regard the cutoff as an epistemic boundary. So what do I mean by that? Well, say you've got some rule for associating physical content with the mathematics of your theory. And now I say, well, I've got this structure in the theory above the cutoff. I told the theory not to worry about it. But now the question is, what's my attitude about that structure if I physically interpret it in the same way as I'm physically interpreting the structure below the cutoff? And one option is just to keep interpreting the structure in the same way. It's still about, say, quantum fields, still characterizing scattering information, etc. On that epistemic reading, the claim of the effective realist turns into the claim that we are warranted to make ontological commitment to the long-distance, low-energy physical content, and that we just should remain agnostic about the short-distance energy physical content. You just get this kind of epistemic boundary. You know what the theory is saying. It's saying the same kinds of things about the physics beyond the cutoff, but we're just to be agnostic about it, or something like that. And on this epistemic reading, nothing about how we attribute physical semantic content to the structure of the theory changes. All it changes is which parts of the physical semantic content we take ourselves to have grounds for believing agree with the world. Okay, this is a standard kind of move in the realism debate. I expect, even if this version of this is new, you can think of something that looks a lot like this. There's exemplars of this kind of view in the literature. I'm characterizing it in a different way, so I'm not going to pin it on anyone in particular. I think James Fraser would be happy for me to pin it on him. He tells me things like this all the time. But what I want to advocate for is another kind of version of the view that actually is the one that I prefer. And I think the advantage that the epistemic version of the view has is that it's relatively clear what it's saying. The semantic view that I'm going to go in for now is requires much more work to fully develop. And so I admit up front that this is not fully worked out. But on the semantic reading of effective realism, we do change how we attribute physical semantic content to the structure of the theory. On this theory, the role of the cutoff functions as doing something like context fixing in a semantic program for attributions of physical content above the cutoff. That cutoff is playing a substantive metasemantic role. It's a place where we're going to change how we read physical content into the structure, the mathematical structures constitutive of the theory. So here's a more humble kind of example that came up in the previous talk. When we ascribe properties like solidity to tables and chairs, those property ascriptions are going to get counted as false if we understand them unrestrictedly in the kind of way that unrestricted property attributions to quantum field systems look on a non-EFT kind of perspective. So what do I mean? Well, if I regard the table from with a resolution of, say, 10 to the minus 2 meters, the table's perfectly well solid. That seems to be a property of the table. But when I initially say the table's solid, that's not the claim I'm making. I've made that claim unrestrictedly. There's no asterisk that says, no, what I really mean is resolved at the level of 10 to the minus 2 meters, it's solid. I mean, it's solid, okay? But there's nothing that prevents us from loading in additional context when we make those property attributions. And if we do that appropriately, there's going to be a perfectly good sense in which it's true that the table in front of you is solid, just not in this unrestricted sort of sense. That sense, as I've just said, tacitly leans on specifying a class of details which don't matter for what we mean by the expression. So if I don't care about the resolving the table to 10 to the minus 8 or 9 meters, where I'm going to start to see the atomic structure of the table creep in, there's just, I can specify a class of details which I don't care about and make that part of the truth conditions for the assertion of the sentence for the sentence that I've asserted. The semantic effective realist, as I'm gesturing at in here, is someone who thinks that the claims of effective field theories are like that. The role that the cutoff is doing is it's telling you something, it's giving you a new place in the mathematical structure of the theory where the way that you're going to associate semantic content with the theory changes. Okay. So unlike the table case though, things are actually better for us, I think, in the effective field theory case because we've got these new tools that I've adverted to. In particular, we have explicit tools for specifying which details don't matter for the meanings of the expressions involving the long distance and low energy content, which are the things that the effective realist wants to be a realist about. Okay. I like this. I know I'm getting close. A couple more. So to whatever extent the project of reading ontology off of physical theories has been successful to date, I think it has to be, at least tacitly, in this kind of attenuated, effective sense. We don't have unrestricted truths yet. And part of what compels me in the direction of the semantic version of the effective realist thesis is that it affords us a way to talk about what the nature of our successes using our scientific language really are like now when we negotiate between our scientific theories and the world today, not at some future hypothetical date. Okay, let me just briefly conclude. So the effective field theory framework gives us new tools for structure specification. It does not dictate how the theory is to be interpreted. At most, it gives us constraints on interpretation because it gives us funny kinds of structures if you're coming from a certain kind of interpretive background, set of background principles. If one offers their own set of interpretive principles, the effective field theory framework provides a principal method for articulating selective realism based on that interpretation. But even with that principled selection criterion in place, there's still a choice point concerning whether to hold fixed one's interpretive principles outside the domain of applicability of the theory. what choice you make there is what determines whether you end up in the one hand on the effective camp or the epistemic camp or the semantic camp. And if you, sorry, that's just what I've said. And finally, let me just connect back to the beginning and say that I think that this seems to me at least to point in the direction of a notion of a reference, which is not the ordinary notion, but it points in the direction of something like a reference notion that's better suited to purpose for discussions of scientific realism that doesn't collapse into the troubles I started with at the beginning. Thanks.
Thank you so much, Michael. I see Carlo, Bill, and Chris there. So Carlo, go.
Sorry.
You don't need you need to project your voice to be heard, and this is just for the camera as before.
Thank you. I follow the account of technical theory the theory. But I'm not sure I grasped your main point, which is your arrival point. Perhaps because maybe I consider myself a realist, but not enough for understanding this distinction you're making. So I mean, we can try to get a bit more clarity. Let's say I hold an epistemic interpretation, and you want this semantic one. Okay. I say, well, I say, yeah, of course, but what do you know about the higher scale? And you say, it seems to me you're going to say, well, I don't know what happened at the higher scale. Yeah. So you're also in the same epistemic situation, or not. So I don't see the difference between the two.
Yeah. That was going to be my question too.
Mine too. Yeah.
Two birds, three birds, one stone. Sorry, bad joke given the conditions at lunch that I followed. If I've got you coming along and you're one of these epistemic effective realists, there's not a ton of there's not a ton of space between us. Where the space is concerns what we take the theory to say about the physical content beyond the cutoff. The effective realist wants to say, I know how to extract physical content from the theory, even in those regimes where I don't have the empirical access. So it's a theory about fields, it says blah, blah, blah. The semantic realist wants to say, at the level of the interpretation, the rules for associating physical content to the theory have changed. And so they want to say, the semantic realist wants to say, and this is the only point of disagreement I take it between the epistemic and the semantic realist, is going to say, the theory doesn't say anything. It doesn't make physical claims about what there is beyond the cutoff scale. It's a language.
I would say there the theory is wrong, and you're saying there the theory doesn't say anything.
The epistemic person, as I've designed them, wants to say, I'm agnostic about what the theory says. It may be right, it may be wrong. I don't know, but I do know what it says.
I want to interpret it just as not saying anything.
Yeah, that's
The semantic version says, the rules for getting physical content onto the mathematical structure of the theory have changed when we go outside the domain of applicability of the theory, delineated by, admittedly, this fuzzy cutoff. And so I'm now saying the language that I'm using is restricted to a specific set of claims about a regime delineated by the cutoff. If I'm the semantic person, I don't think I've given you a language that talks about the regime outside of that boundary. The epistemic person thinks that they've got a language that talks about stuff outside that boundary. It's just that their epistemic attitude about what the theory says about that is that they're going to be agnostic about them.
Just to a clarification, a finger. So the reason why we don't worry about what's beyond the cutoff is that in the example you were proposing is that we do have a theory that works beyond that. So in the case of the continuous limit of quantum field theory, well, you will have some classical theory there that works, right?
So in the depends which limit we're talking about. So in the missing UV completion of the standard model, say, I take it we don't have agreement at least about what the theory is there. It's supposed to be there that works, and none of what I'm saying here is supposed to remedy that fact. It's rather to solve a pretty different problem. It's to solve the problem of saying, I've got this really empirically successful theory. It's restricted, its empirical success, as we've been able to test the theory, lives in a pretty specific band of what our empirical access to the world is like. I want a full-blooded scientific realism that is as realist can be, but where that realism is coordinated with the nature of the empirical access to the world that I've got.
Yeah.
And the worry is that certain kinds of thinking about these various stages, from interpretation to from structure to interpretation to realism, load in maybe through the back door, maybe by accident, maybe not even on purpose, this idea that that what it would have been to give a full-blooded realism requires this kind of unrestricted thing. And if you then get handed a theory like the standard model, where we've got evidence to think that it can't be that unrestricted thing, then it's like, uh-oh, the rug has gotten pulled out from under us. And all of this is just an effort to say something which I think everybody should want to say in one or another of the versions that I've presented it, which is that no, we should just be as realists can get about the parts of what the theory says that we've got empirical access to.
I have I have more questions, but there is a long queue of people. So the next one is Chris there.
Great, thanks for your talk. I'm glad you're pushing on the effective realist to address some of these pretty central, big picture kind of questions. I mean, there seem to be some downsides to the semantic proposal, if I understand it correctly. At least if we imagine an effective realist trying to go back to other sorts of scientific theories. I mean, in this case, if I understand, in the core motivating case, there's some reason to think that things really break down at various scales. And so now there's sort of a reason why the words would the words would no longer have their meaning. They would just sort of, the whole thing would just not make sense anymore. But in other cases, like I just think of very simplistic cases, like we're talking about fluids, and we distinguish different sorts of fluids and the ways that they behave in various regimes. And I mean, are we going to? Is there any similar motivation for saying that? Well, as we do that, we're changing the meanings of the words, and now actually we're not talking about like the word fluid has lost its meaning if we go over here. So I guess that would be the sort of, is there a way to think about the meanings of words where sort of systematically things would match up in the way that the effective realist wants? I don't know.
Yeah, so, okay, so two strands, both very interested. Let me try to get a faithful reconstruction of what happened in the first part, and then I'll come to the second. So, it's true that part of what's being acknowledged here is that we expect aspects of the description that we give in the limited regime where we are being realists to break down in some sense. So I think that the scientific language that is being developed for the specific collection of this specific tranche of reality is eventually going to break, or at least I put even odds on it breaking. Probably put better than even odds on it. The whole purpose of the semantic kind of revision program is to coordinate meanings for the terms in such a way where we don't get into these reference failures down the line once we carry the application of the terms outside of the boundary of their applicability that we originally delineated. So we're trying to get out, basically, the idea is try to get out in front of the problem, to try to get out in front of the fact that eventually we don't expect, or we don't feel like we have grounds to expect at least, that our words are going to have this always and forever validity when applied in contexts beyond those where we've tried to use them. The fluids case is very interesting. As I said briefly in the middle, just as an aside, eventually I think this kind of thesis can be exported wherever you like in scientific language. You might lose some of the explicit tools that you have for demonstrating the kind of insensitivity to shorter distance structure because they don't apply in that case. In the fluids case, there are analogs of some of the tools. So we can talk in more detail about the specific case you have in mind. But in general, the procedure is one according to which we're trying to safeguard the validity of our uses of language by constraining it and not making it more expansive.
Okay. Oh, thank you.
You're getting a lot of questions, so I encourage shorter questions and shorter answers. Let's see how many, if we can get to the end. The next one is Simon.
Yes, thank you. Thank you. I mean, many thanks, but I would welcome a simple example where effective realism has something distinctive to say. So can I just give you the example of non-relativistic quantum mechanics? What does effective realism say there? You're looking for a full-blooded realism, remember?
Yeah, so, I mean, this, to be fair, I think I told you very early that the tools of effective realism don't do much at all to dictate what your principles of interpretation are supposed to look like. So the tools, as I've presented them to you in the end, that you get in the effective field theory framework, are tools for studying how relatively, how the physics of different scales are dependent on one another.
I meant effective realism, not effective field theory. I'm asking, what does effective realism have to say about non-relativistic quantum mechanics?
Well, by itself, it's not a tool that's designed to...
What further ingredients do you need me to supply before you'll say anything?
I need you to tell me. Knowing you, or knowing some things about you, I can kind of work backwards and work out what, certain features of what physical content you in particular want to load on top of the mathematical structures constitutive of non-relativistic.
But I'm open-minded. I mean, don't put me down as an Everettian. I'll accept hidden variables. I'll accept...
No, but so...
Just go for it, you know, but what are you going to say?
Well, what I'm saying is there's nothing about the effective realist thesis that's going to adjudicate between any of those. You have to...
What more do you want from me then?
Well, so... if you want to get an effective realist construal of non-relativistic quantum mechanics, you've got to feed in what the structures are. In the case of non-relativistic quantum mechanics, those are relatively well agreed upon. You've got to feed in what your rules for assigning physical content to those structures are. There, if you hold the room, we're going to go in roughly 50 different directions. And then if you load the effectiveness on top of that, that thesis by the effective realist thesis isn't going to be of much help in solving the issues. The issues in the non-relativistic quantum mechanics case unfold at the level of getting from the mathematics of the theory, which are relatively well agreed upon, to the physical content. The issue there, at least as the non-relativistic quantum mechanics is debated, has not been about extending non-relativistic quantum mechanics outside of its domain of applicability or something like that. Well, I mean, I guess I don't want to have said that because there are versions of debates that do have that character. What I'm trying to tell you is just that the tools that I've got on offer are solving a different problem that presuppose that you've already loaded in a rule for getting from structure to physical content. So what the kinds of things that we call, I know I'm not giving a short answer, the kinds of things that we call interpretations in that case, you have to have an interpretive rule, and different people have different ones. And so
Well, we all have the Born rule, one way or another.
sure.
But look, I don't want to monopolize this. I mean, there are other questions.
Other.
Sorry.
Thanks. This is really interesting. You know, we've talked a lot about this before, but I wonder. So when you're kind of gesturing towards this being more broadly applicable outside of the context of quantum field theory, I worry that sometimes we might get too narrow about what the domain restrictions are. Like in quantum field theory, we have, okay, below some energy scale, and that, I mean, people sometimes talk as though that's the, you know, be all end all, or distance scale is the be all end all, sort of equivalently, of where we delimit the applicability of theories. But, you know, a lot of theories outside of the context of fundamental physics, you might have temperature limitations, you might have the speed at which something is moving relative to something. Like there's all these other domain restrictions that might be relevant, and that we might, even within the context of quantum field theory, maybe by the lights of string theory or quantum gravity or something else, we might be missing out on. And so I wonder how safeguarded we are really against these referential failures, right? So, you know, there's a sense in which we might only be restricting parts of the theory, and that might be good, but we might be missing other restrictions that we can't see unless we know what the details of how that theory kind of work out are.
Yeah, it's a completely valid worry. I don't, so you're completely right that the cutoff is just one particular example of the way that you might go about delimiting boundary of applicability. I guess the core spirit of your worry is like, how can we know that we've succeeded in that? In terms of giving our terms semantic underpinnings that we think are safe. I guess I would be hesitant if I could give you an argument that said they were hermetically sealed once and for all and we couldn't fail. That, I think, would be an indication that we've been too restrictive and too cautious in how we're thinking about the truth conditions for our sentences. So I want the view to be one which sticks its neck out, which could be wrong, and which could stand in need of revision down the line. The aim is to develop a way of talking about what the ontological commitments are, which appropriates the insight that under certain special conditions, we do get good arguments that we are relatively insensitive from wide classes of phenomena. That's the core spirit of it. That can be done with different kinds of boundaries, and I don't want to push it to the point where I demand so much of those arguments that they ensure that they can never fail in the future.
Mike?
Thanks. So if even I've understood everything correctly, putting specific examples from quantum field theory aside, like if I put my general philosophy of science hat on, I'm very sympathetic to what you want to call effective semantic realism. But I was wondering if you could come back to the beginning a little bit. So I was wondering, because you mentioned that there's some disagreements with Stein. And I'm curious exactly how you construe this, because that didn't really come out during the talk as much as
I'm hanging my hat on semantic contents, which, at least in that particular paper, Stein repeatedly suggests is kind of like missing the point or not what's most important or something like that. So I'm like retaining some kind of revised notion of reference of the terms actually delimiting some class. He, in that paper in particular, is quite consistent. To be fair, the notion of reference is the one at issue in Quine. And Quine is his example of the referential realist that he's dismissing and setting aside and saying has missed the point. There's nothing about what, I've also got, the kinds of semantic revision that I'm appealing to are going to require just setting all of that kind of manner of thinking about reference aside as well. The whatever kind of referential realism the gestures I'm making might eventually point to, it's going to be distinct from the one that Stein is dismissing. The difference from Stein is just that in the end I am insisting that there is a referential type relation that is the interesting one that I want to cash out my realism in terms of. Thank you.
Jim.
I was afraid this might happen. I have two questions. One short and one slightly longer, and you can choose to do with them as you like. So the short one is, in responding to Carlo and some of the discussion following it, you said that the semantic, several people tried to say, so you're saying that the semantic effective realist wants to say that the theory doesn't say anything beyond the cutoff, and you kept saying, no, the rules change. And so the question is, what are the new rules?
Right.
And then the second question is, and this is also a theme from Stein, that in many cases of where sort of scientists with their humors in the appropriate balance were able to do something successful, it involved a kind of novel extrapolation of current theoretical ideas into contexts that people hadn't really thought they should apply before, sort of taking them seriously in a way that maybe the originators of the ideas or earlier physicists didn't. I'm worried that by building the effectiveness into the realism, you're taking away from realism the thing that made realism fruitful from Stein's point of view of you have to have sort of these humors. Sometimes you have to be more realist, sometimes more instrumentalist, and sort of having the judgment in various contexts is the important thing.
Yeah. Yeah, so to finish my answer, Mike, what Jim said is exactly what Stein thinks is the important thing, and you can set aside this business about the referential stuff. So yeah, point taken on that front. On the first front, I guess what I want to say is. What I've been trying to do here is to put structure on a space of views. I can give you versions where the rules do change, and there's new rules, and there is semantic content, and they play differently with some of those new rules play differently with the domain of the introduction of a domain of applicability than others. And there's going to be versions where you could take the theory not to talk about what's out there. Those are all, according to the way I've carved up the space, going to amount to a version of the semantic turn. I'm happy to consider various of them. I'm hesitant. The reason I was balking about any version that says the theory doesn't say anything at all is because inevitably the way that we generate these boundaries is not sharp. We move them. It's pragmatically important in the way that we use the theory to be able to move them. And so the rules, I'm assuming any plausible collection of rules are going to have to be responsive to that fact, and so I don't want to rule out any kind of rules that are responsive to moving cutoffs and things like that. So it's a space of views. There's room for both of those inside of it. I think eventually to be able to do justice to all of the kinds of ways we manipulate structure when we formulate effective field theories, the rules are probably going to have to be operative outside strictly. Well, there's not going to be a strict point at which to say now we don't say anything anymore.
Chris?
Yeah, so I was really thinking about a specific case of the rules changing to see that might be a relatively minor case, but in precision measurements of QED, something that Adam and I have thought about, and Adam can correct me if I say anything incorrect. You have people use like a pinning trap and trap a single electron or a single positron. And with the level of precision that people are able to reach with that, you might think a single electron is something that's perfectly describable just using QED. It turns out they can reach a level of precision that you actually have to treat it using the full standard model to get a calculation that's in agreement with observations. So would that involve, so you could initially treat QED as an EFT, and then you're shifting to a context where you're now treating that system as a standard model system. How would that involve like a shift in the semantic rules on your view?
Yeah, so these are precisely the kinds of cases that I'm worried about. Schwinger sits down to calculate the first perturbative correction, the anomalous magnetic moment of the electron. The physical system in his mind is electromagnetic field, which in particular the coupling of electron to a photon. The other stuff that eventually gets loaded into QED, the other ontological stuff that eventually gets loaded in, is not part of what he's thinking about, and the rest of the standard model certainly is not in what he's thinking about. So the physical thing that he's talking about, when considered as part of the world, we now know is like only a partial characterization of the physical system that he was actually, like the people who were doing the experiments, Christian Foley, were measuring. And I think in cases like this, we want a story according to which Schwinger is eventually making true claims about the way the electron and photon couple to one another, but which eventually turn out to be sensitive to the couplings to other fields, which we're not yet known about. The shift, the kind of shift that's going there, involves things like what kinds of properties do we assign to the electron? What is the modal profile of the electron? So and so on. So what kinds of relations does the electron bear to other particles, what have you? So what I'm imagining is a case where when we have a term like electron, we're doing this boundary delimitation, and we want to be able to we want to delimit the boundary of the way we're applying the term in such a way that it can grow as we learn more and we come to have more detailed understanding of the properties of the entities in question, the modal profiles of the entities in question, and so on. And so as we progress, the restriction on the realism is designed to make it such that Schwinger can be talking truthfully about how electrons couple to photons, even in view of the fact that he didn't have an exhaustive characterizations of all of the ways that electron, the QED and standard model couplings fit together. I want a view of that, of the term electron, which can expand as we fill out the modal profile. Yeah.
I am Wayne and Eric. I hope. Can you do quick?
Eric hasn't asked a question yet, so let him go.
Thanks so much. So thanks, that's great. I have a more general philosophy of sciencey sort of question. So I'm super sympathetic, but I wonder if there's a kind of worry about the story you're going, which is that it leaves the door open to people sort of salvaging any kind of theory they want by just constraining the boundary conditions, right? So you can imagine someone coming along and saying, phlogiston theory was always right. And someone says, well, look, it turns out that theory is really good at describing things when things are set up artificially in really, really constrained settings. the second you change that, it falls apart. And I'm like, oh, that's fine. It's just only designed to be worked in these really constrained situations. So yeah, of course it's true. It's the ontology is right. We're realists. It's just that as soon as you move out of the conditions in which it's successful, the rules change. Right? Now there it seems like almost any theory you like, you can get a realism out just so long as you constrain the boundary conditions in the right kind of way to the conditions under which it's successful. Right? Now someone else can come along and say, well, look, my theory can. The problem is we want something that can account what the system's going to do under all different kinds of situations. And my theory does that. I say, yeah, you want an unconstrained, unbounded version of realism. But we don't need that. So it seems that what you can, the intuition, it seems that sort of justifies the unbounded notion is, yeah, we don't want to just sort of arbitrarily dictate the boundary conditions of the model to fit with those in which it's successful, because then any theory can work. But if you accept an unbounded realism, you can block that sort of problem. So I don't want to say I'm taking that view, but I think there's a kind of intuitive pull there. I'm just curious what you want to say about like how to sort of push back against this notion of like, yeah, you can just make anything work if you just constrain it, the boundary conditions.
Yeah, I guess there's a version of that worry that I'm not super concerned with, but there's like a trivialization you can do, which is like, you give me a body of claims, and I can come up with a way of making all of the claims true according to my semantics.
Yeah. We're realists. There's one can be realist.
And the thing that's constraining things here, and so it's certainly true that you can go in that direction. Like given the conceptual pieces that I've introduced here to do the kind of thing that I want to do, there's no doubt that you can go in that direction. I do think then at the end of the day, you're going to have to take a given effective realist construal of a given theory. And remember, I said that part of the virtue of the view is that we're bringing ontological commitment in line with what we have direct empirical evidence for. And if the situation you're describing is a kind of trivialization where the empirical evidence is paper thin, where I haven't been able to confront the world repeatedly in a way that gives me grounds for thinking that the semantic content that I voted into the theory does match onto it outside of some very, very restricted circumstances, then, okay, perhaps there is a realism about some very thin tranche of reality. And I guess in the end, if that's the way this turns out, then there turn out to be some theories where we have an enormous amount of empirical evidence, at least within a given tranche of the space of possible measured values of things, as in the case of the standard model, and that amounts to a robust kind of realist commitment. And there's other cases where the effective realism looks much thinner. I'm not particularly worried about that. The quality of the evidence, I think, should dictate how realist we are, and part of the view is supposed to be capturing that fact.
Awesome. Thank you.
Thank you, Mike. So it's time to move to the coffee. We have a bit less than 50 minutes. We start again at 4 o'clock. Before going to that, let's start.